Welcome back, Nature in Code. We're in chapter 6, and we just learned about evolution by natural selection. And you now understand how evolution by natural selection works. It's quite simple. Genotypes with higher fitness have a higher probability of surviving and reproducing, and therefore they have a higher chance of passing on their alleles to the next generations. And so over the generation, those alleles and genotypes become more frequent. As we've seen, much can depend on exactly what the fitnesses are, depending on how the alleles are packaged together. Now, we haven't talked much about fitness, though. We simply mentioned earlier that it is the ability to survive and reproduce. But what makes an allele or an individual better at surviving and reproducing? Well, you can think of a few examples. So, for example, an animal may survive better because it is harder to be spotted by a predator. So, if you have some sort of prey here, some animal, and then you have a predator here, well, if that prey now manages to somehow make it harder to be spotted, some allele that causes this prey to be harder to be spotted by the predator, it will now have a higher fitness because its probability of surviving increases if it avoids predation, and therefore we expect that allele, to become more frequent due to natural selection. Vice versa, you can imagine that you have a predator, some animal that maybe has a better sense to locate its prey, or can just spot the prey much better, and as a consequence, that animal now has a higher probability of survival, and thus, whatever the allele is that causes this trait or that influences this trait, it will enjoy a larger fitness. And so that's the basic idea. Now, often, the environment in that context is the abiotic environment. For example, an animal or a plant could survive better because it could deal with harsher climates. Now, that's simply sort of an adaptation to a climate which is abiotic. However, in many cases, we have a situation like this where the fitness of one species depends on what the other species does. And if you have that, then you quite often get something that is called co-evolution, because now the species is not just evolving to sort of adapt to its abiotic environment, but it's actually evolving to adapt to its biotic environment. And if that biotic environment is another species, well, that species is also under selection. And if the interests of those species are opposed to each other, as is the case in predator and prey, then you can get a situation where this coevolution can lead to very fascinating cyclical dynamics. And I'm going to make another example here, not predator and prey, but hosts and parasites. So, parasitic life is extremely common. Almost any species has many, many parasites. And so, I'm just now drawing a human here. And, that human might get infected by, some parasite, a virus or a bacteria or what have you, that causes some sickness. Now, the fitness of this host due to the sickness will decrease, right? Because if you're sick, you're weak, and that means usually, lower, in evolutionary terms, a lower chance of survival, a lower chance of reproduction. From the parasite's perspective, though, what just happened is great, right? Getting into a host is often an absolute requirement for a parasite to reproduce. Many parasitic species are not able to reproduce outside of a host. They need a host to be able to reproduce. So, getting into a host is a requirement, and then being passed on to the next host as well. So, this host may now infect another host, whose fitness then, of course, will also go down. However, there may be a case where you have another host here, and that host maybe carries an allele that makes it harder or potentially impossible for the parasite to get in. So the parasite, may try to transmit, but will perhaps fail because of the genetics of this host. And now you can imagine that this is really bad news for the parasite fitness. Again, because the parasite cannot reproduce without the host. So in terms of fitness for the parasite, that has just decreased quite dramatically. On the other hand, that host, compared to that host here, has a fitness that is increased because it doesn't get sick, and therefore compared to the sick host, its chances, of surviving and reproducing are higher. So this is another example where you can clearly see that, the interest of two species are exactly opposed. The parasite would like to infect you, or infect the host, but the host would like to not get infected. And when I say like, it's meant in a sense that is very common in, when you talk about evolution. No one likes anything or wants anything. It's just that if your fitness is low, that just automatically means that the alleles that you carry will be less frequent on average, down the generations than if you have alleles that give you a high fitness. And so, fitnesses will increase or decrease due to fitness. It's not that anyone really wants or has to want anything for that to happen. But it's, it makes it easier to talk about these things if we can sort of, use that, humanized language. Okay, so this is a phenomenon that's really interesting and that leads to coevolutionary cycles. And what I want to do now is I want to formalize this a little more and then go ahead and implement this in JavaScript. So what is the simplest example we can come up with? Well, the simplest example is that we have a host, and that host can have one of two alleles, a 1 or a 2. And we're now going to simplify our old model with diploid individuals quite a bit by assuming we just have haploid individuals. So only one allele. No A1A1, no A1A2, no A2A2. It's simply there are only two possible genotypes. It's either A1 or A2. The same model, of course, would work with diploids as well, but since we now have two species, I want to make this model as simple as possible. So the parasite could also have an A1 and an A2 genotype in the simplest case. And now we can, of course, say, depending on these genotypes, the outcome will be different. And the simplest model we can come up with is that of a sort of a key lock mechanism. So let's say the A1 parasite can infect the A1 host. So this is infection here, and the A2 parasite can infect the A2 host because they have the correct key, so to speak. But A2 cannot infect A1, and A1 cannot infect A2. And you can now imagine what will happen here over time, right? Let's say, A1 is very common. Well, as a consequence, A2 has a low fitness, on average in the host population. Because a high fitness, because A1 cannot infect A2, and so A2 will have a high fitness and increase in frequency, and potentially even, perhaps take over or almost go to fixation. Now, that's great for this A2 host, but it's not great for this A1 parasite, right? Because the A1 cannot infect the A2 host. However, the A2 parasite can. And so, in the parasite population, the A2 parasite has now a much higher fitness than the A1 parasite. So the A2 parasite will increase in frequency because it can infect the common host here. Now, as a consequence, the A1 is really having a great time, the A1 host, because it cannot get infected by this really successful A2 parasite. And then as a consequence, the A1 parasite will again increase in frequency because now that the A1 host is common, it will enjoy a high frequency, a high fitness, and thus increase in frequency, and so on. So this is a So cyclical dynamics, you can kind of think of it as an arms race, where one species responds to what the other species does in terms of its genetics, and then as a consequence, the other species will respond to what what the first species has done. And this is an arms race that can lead to these co-evolutionary cycles. And what's important here is that we have something that we call negative frequency dependent selection. What does that mean? Negative frequency dependent selection. Negative frequency dependent selection. Dependent selection. Okay, so there are two things here. It's frequency dependent and it's negative. So let's look at this first. Frequency dependent simply means that your fitness does not just depend on your genotype, on your own genotype, but also of the genotype of the other players in the system. That's what frequency dependent means. And negative frequency dependence means that a genotype will be less fit when it is more common and more fit when it is less common. You can also come up with an example of a positive frequency dependent selection where you're less fit when you're less common and more fit when you're more common. But that is rare. And in these antagonistic interactions, you usually have negative frequency dependent selection. And I've just given an example, right? When A1 is rare, that as a consequence means that the A1 host here really has a benefit because it gets infected by A1, but A1 is rare. And A2 is common, and the A1 host cannot get infected by the A2 parasite. So the A1 host will increase in frequency, which is great news for this parasite here, right? Because it can infect A1. So here's an example of a rare parasite now having a benefit due to its rareness. Vice versa, if the A1 is very common, that will drive the host population to move over to A2, and that is now bad news for the A1 parasite. So because it is common, population will shift here, the host population, in a way that is bad for the parasite A1. So this is negative frequency dependent. You benefit from being rare, but then as you become more common, you don't benefit anymore, and you're in fact negatively affected. Now, let's go ahead and implement this simple host parasite model in JavaScript. So before we can do that, we need to formalize this a little more, and we'll do this in the next video. See you in the next video.